Hi, everyone. This is Jason Key with SB Grid at Harvard Medical School in Boston. Thanks for joining. So this month, we're lucky enough that we've got Scheres joining us from the MRC in Oxford. So Sjors' lab has sort of led the charge into maximum likelihood classification of cryo-EM data. So his lab recently published a paper of a ryanodine receptor in Nature in January. That was about 3.8 angstroms, I think. So Sjors is the developer of Relion, and Relion takes advantage of the statistical treatment of cryo-EM data to both simplify the processing by extracting the parameters sort of as directly as possible from the data, but also sort of deconvolute heterogeneity in the data itself. So with that, I'll turn it over to you, Sjors. So go right ahead.
Thank you, Jason, for your introduction. That was almost everything was correct except that we're in Cambridge, not in Oxford.
Oh, apologies.
No worries. Yeah, so I will discuss the use of Relion in a second part of my talk, but I thought I'd first describe the type of problem that we have, and then describe two aspects of that problem: its incompleteness and its ill-postedness, and how Relion deals with that, and how that's perhaps different from other approaches. So those two aspects are incompleteness and ill-postedness. So the incompleteness is the maximum likelihood part of Relion. Similar approaches were used previously in ML 2D and 3D approaches in XMIP. Then the ill-postedness part of the problem, that's specifically relevant for Relion. So that's new compared to the XMIP approaches. Okay, so if we look at cryo single particle analysis, there's a few experimental inconveniences. First of all, the electrons damage the biological material, so we have to be careful with how many electrons we put on them, use low dose, and that means we have images with large amounts of noise. Secondly, we need to defocus to get contrast, so we get all kinds of artifacts in our imaging process, and we typically describe those by the contrast transfer function, or CTF. And then finally, because we have a solution of macromolecules that tumble around in solution, but the moment that we freeze it, we cannot control the relative orientations of all these particles. So that means we have unknown orientations of projection views of copies of particles that also not necessarily have to be all in the same three-dimensional structural states, as compositional or conformational heterogeneity may lead to the presence of multiple 3D structures in your sample. So from a more theoretical point of view, that then leads to an incomplete ill-post inverse problem. So the inverseness of the problem is, you can basically, that's many of the problems in sciences, you can think of them as a problem that in two ways. There's a forward way, the forward model, which in our case, if you know the three-dimensional structure, for example, VK in this notation, then you can calculate in the computer projections, two-dimensional projection images of such a three-dimensional map in a direction phi, for example. That's the operator p phi. And then because we have good models for what the effects of CTF are on our images, we can then convolute our projection images with the CTF, and then we could simulate some noise in the images, and we could get a pretty good representation of our experimental data. So that's called the forward model, and the parameters for that model are relatively well understood. Now, the inverseness of our problem is that we don't have the three-dimensional map, and we want to calculate experimental images. We have to go backwards. We have observed our two-dimensional projection images, and without knowing phi, we now have to calculate all these two-dimensional projections back into a 3D reconstruction, and that's much more difficult. So before we go any further, I thought it would be useful to introduce projection slice theorem for those of you who are not aware of this, because it helps thinking in real and reciprocal space. So if you have a three-dimensional map like the one on the lower on the upper left here, then you can calculate its three-dimensional Fourier transform, and that's just a mathematical operation. You go back and forth, and it's just a different expression of the information in real space or in Fourier space. The Fourier space being a summation of all many sine waves. Now, a two-dimensional projection of the three-dimensional map here, for example, in the direction of these red dotted line, it gives you then a two-dimensional projection image. And for a two-dimensional projection image, you can do the same as for the three-dimensional map, that is calculate the Fourier transform. And again, you can go back and forth between Fourier space and real space. And it's just a mathematical expression, and the Fourier space you can think of as just an alternative representation of the same amount of data, of the same type of data. Now, the projection slice theorem states that the projection in this direction of the real space map that gives rise to this 2D projection, the two-dimensional Fourier transform of that projection is a central slice through the 3D transform of the 3D object, and the direction of the slice is then perpendicular to the direction of the actual projection direction. So I think that's, perhaps for those of you outside Cryon, makes it easier to understand how that if you have many different two-dimensional projection images, you can actually go back to a three-dimensional reconstruction of your particles. Because what you do, if you would know all the relative orientations of all the different projection directions of these 2D images, you would basically fill up this three-dimensional Fourier transforms with two-dimensional slices in many different directions. And then you could do an inverse transform to get to a 3D reconstruction of your object. Good. So our data model, we then have a choice of doing our calculations in the real space or in the Fourier space. And in principle, they're equivalent, although each space has its own advantages over the other one. Characteristics are that in the real space, the actual projection operation is like integrals, line integrals, according to those dotted arrows that I showed in the previous slide. So the CTF acts on projections of the 3D map as a convolution operation. Now, in the Fourier space, this projection operator, as I just explained, takes on the form of just taking a two-dimensional slice out of a three-dimensional transform, so that's different. And another difference is that the convolution of the CTF in real space becomes a multiplication with the CTF in Fourier space. And then you could describe noise in both spaces. Now, in XMIP, ML2D and ML3D are based on a real space data model, whereas in Relion and also in old XMIP MLF programs, the actual data model is in the Fourier space. And I'll come back to that about some of the implications. Now, both XMIP and Relion share the way how they deal with the incompleteness of the program. So what's incompleteness? And to illustrate the incomplete problem, I'd prefer to use a simpler problem first, and that's two-dimensional averaging of a single class of projection images. So imagine you have a very strong preferred orientation. You only get top views of your molecule. There's no CTFs for now, and then we just need to align all those top views and average them together. So in this case, you have a two-dimensional image A, which is rotated in many different instances, and noise is added, and you get many different experimental images. Okay, so incomplete data problems are, you could think of them as problems where part of the data was not observed experimentally. And in our case, these are, you could think of this incomplete part of the data being the relative orientations of all the experimental particles. And if there were to be 2D or 3D heterogeneity, then also class assignment would be part of the incompleteness. Now, in general, these incomplete problems are relatively difficult to solve. Often people use iterative methods, although not necessarily. But the common characteristics is, and that's the usefulness of thinking about this, if the data problem were to be complete, then it would be very easy to solve. Another famous incomplete data problem out there in structural biology that many of you may be aware of is then the phase problem in X-ray diffraction. Because in X-ray diffraction, you only observe intensities of diffraction spots, which relate to the amplitudes of the Fourier components, but the phases of those components are completely lost. So the phase problem in X-ray diffraction is in some extent analogous to our orientational or class assignment problem in single particle analysis. So, for example, of our no CTF two-dimensional averaging test case of these penguin images, these are the observed data, X, and there is missing data, Y, which are the relative orientations of all these penguins. If oh dear, if you don't know these relative orientations, then it's not necessarily easy to calculate the average structure. You would first need to align all the penguin images. If you were to have a complete data problem and there's no missing orientations, for example, because all the penguins are facing in the same direction, perhaps they form a 2D crystal, then it's very easy to estimate the underlying signal in the images just by straightforward taking the average of them. So that would be easy. Now, what do you do if you have an incomplete data problem? Conventionally in the field, what many people have done is the first of two options, is to add the missing parameters of the problem to the actual model. So no longer am I only interested in finding the underlying signal of the penguin, I'm also becoming interested in finding the relative orientations of each of the penguin images. And the second option is one where you marginalize over all these missing data, and it happens in a statistical manner where you calculate the probability of observing the data regardless of what any of those missing parameters would have been, and you do that by integrating them out. So you calculate probabilities for each of them and you integrate them out. Now, the first option in cryo-EM field has typically been called maximum cross-correlation. In X-ray diffraction, people have called this least squares approaches. And in cryo-EM, both cryo-EM and X-ray diffraction techniques have called the second option maximum likelihood techniques. So let's have a look at the maximum cross-correlation approach first. If we would have some initial guess about our penguin signal, and we can come back on how you could get there, then what you could do, you could calculate for each different orientation of experimental image with this reference a figure of merit, and people have used this cross-correlation or cross-correlation coefficient, and then you just rotate your experimental particle or your reference particle around until you find an optimal fit. You calculate the cross-correlation for all these rotations. And then what you do, you say, oh, where it fits best, that will be the true relative orientation of your experimental particle with respect to that reference image. And then what you do this not for one experimental image, you do this for all of them. And because your initial image of the penguin was a relatively poor one, this alignment process, as people call it, is not perfect, but it will be better than the more or less random orientations that the particle were in. So that if you average over the now more or less aligned particles, we'll get a better impression of our underlying penguin image. And that then makes it clear this process becomes iterative, because if we use that reference, that improved penguin as a new reference, then the assigned angles will be better. And at some point, they will become perfect, so we can calculate the best possible estimate for the pinwing image. Okay, so the maximum likelihood approach to this very problem of single reference to the alignment in real, and this implementation was in real space, was actually introduced to the field by Fred Sigbert at Yale, and that already happened in 1998. So the maximum likelihood approach is different in this marginalization over all the possible orientations. So what you do for a experimental image, you compare it again to a initial estimate that you have of the underlying signal in your image. And you use then a statistical model of the data, and Fred proposed a model in real space where each real space pixel is completely independent from the other, and he assumed that the noise in each pixel would be Gaussian distributed with mean zero and a standard deviation that you could estimate from the data. So you use this Gaussian data model to calculate a probability of observing that image in a given orientation relative to the estimate of the underlying signal, which would be theta, would be the fuzzy pinwing image here. Now, you can do this for, and it's important to notice that the Gaussian function inside the exponent of the Gaussian function is a square difference term, and a square difference term is very closely related to cross correlation. Now you can calculate this probability not just for this orientation, but again you could rotate x around or a the other way around and calculate the same, doing these comparisons and calculating a probability for this particular experimental image in all possible rotations phi. And I've tried to express that in this figure here. So this is the first experimental image. If I have the pinwing on its side, then the probability that I would observe the image in this orientation, given that this would be the correct reference, is relatively low because the pinwing on its side and the upside up reference do not match very well. And I've tried to express that as a rather transparent picture of the pinwing. So then I start rotating my pinwing around, and when it goes upside up, then it will resemble much better the template image. The square difference will be lower, and the probability will be higher in the Gaussian function, so that the image is less transparent. Now, the main difference that results from this marginalization is that rather than saying this is the correct orientation of this particle and it will only go into the average for the next iteration in this orientation, you do something else. You calculate a probability weighted assignment of all these different orientations. So you can calculate the average for the next iteration as probability weighted averages over all particles in all possible orientations, so that you get a two-dimensional array here of all these little images, and they each go into the average with their weight, which is related to how transparent they are. And then this process is equally iterative as the other one in the case of the maximum cross-correlation approach, because this image will be better. You can put it back in here, then the probability distributions that you will calculate will be better because it will resemble the reference resembles the true signal better. So at some point you hope to converge again onto the same best possible estimate of the signal in your data. Now, an intuitive way that I like to think about why that would be a good idea is that if there is a lot of noise in your experimental images, then the best possible orientation based on the maximum cross-correlation target alone could be noisy. So you start making mistakes that are based on the high levels of noise in the images. The maximum likelihood approach will estimate how much noise there is. If there is much more noise than signal, then to distinguish different orientations of the particles, then rather than saying, oh, this is the correct one, you start to assign rather similar probabilities to multiple different orientations. And that has some kind of a more conservative effect, if you like, on the convergence of the of the refinement algorithm, and therefore is then becomes also less likely to fall into local minima. Okay, so does that mean that these two methods are then completely different? No, actually, because of the similarity between the square difference term in the Gaussian function and the cross-correlation coefficient, in the limit of noiseless data, then the two techniques actually become exactly equivalent. Together with Fred, we wrote a review paper in methods in enzymology. So if you'd like to read more about how to deal with incomplete data problems by marginalization in Cryo-EM, then I would recommend reading up on that one. That brings me then to the second aspect of the problem in single particle analysis, which is the ill-posedness. Sorry. So maximum likelihood estimators, you can show that under certain conditions are the best you can do, but one of those conditions is then that the data set needs to be infinitely large. That's never true. Even if you use Legend-on or EPU to collect your data, it will always be limited in size. So the bad news with that, if you have a limited size data set that is noisy, then there will not be a single estimate, a unique solution to the problem based on the experimental data alone. Instead of that, there will be many noisy solutions that describe the data equally well. That opens the door to all kinds of problems in overinterpretation of your maps, etc. The good news is that you can use external information to supplement the experimental information, and then you can pose an alternative problem for which one unique solution does exist. This is called regularization in a general sense. If you think about conventional approaches in cryo-EM single particle analysis, then both Wiener filtering and low-pass filtering you could consider as regularization approaches, although to some extent ad hoc ones. So a typical refinement procedure, and I'm skipping over gold standard procedures for now, you'd have an initial low resolution reference, and you align your particles to the reference, then you do a reconstruction. Now this reconstruction often will be very noisy. Then you do some kind of low pass filtering, for example, based on an FSC curve, but people have done all kind of ad hoc things. Before you use this reconstruction as a reference in the next iteration. And the reason why you have to filter is that if you don't filter, then high frequencies will start to accumulate in your reference, and they will start to drive the actual alignment, and things will go completely haywire. So these kind of ad hoc regularizations have been very common in the field, and it is because you absolutely need to regularize your problem, otherwise you will start running into problems. Okay. Now, the statistical approach provides an alternative view on the regularization problem in terms of a Bayesian interpretation. And Bayes' law says that the probability of a model being the correct one, given your experimental data, is the likelihood function, which is the probability of observing the data given the model, times a prior, which is the probability of the model in the absence of any data, divided by the evidence, which is the probability of observing your data. Now, because you have already observed your data, when you get to analyze it, the probability of observing your data becomes you could consider it a constant. It's irrelevant. So you can pose a problem which is no longer just maximizing a likelihood function, which we've been doing until thus far. You can multiply that likelihood function by a prior, and that way you get a regularized likelihood target, which is proportional to the posterior. So it will actually optimize the probability of having the correct model giving the experimental data, which is exactly what we want to do. So this is called regularized likelihood optimization, and that's where the name Relion comes from. Relion. Okay, so then what do you use for the likelihood function and the prior? So the likelihood function is now in Fourier space, because this is about Relion, so where Fred's approach and also my own old ML 2D and 3D approaches in XMIP assumed Gaussian noise that was independent between real space pixels. Relion assumes that noise is Gaussian and independent between different Fourier components of the experimental images. And you can, because you work in Fourier space, you can estimate the amount of noise for each Fourier pixel as a function of the spatial frequency nu. And that way you can actually model noise that is correlated in the real space domain. And this is then just the expression. It's a multiplication over all Fourier components J of Gaussian functions, where here you have the square difference terms inside the exponential. So it's just like the data model I showed you before, the experimental images, each Fourier component J is compared to the J component of a 2D slice taken out of the 3D map in a given orientation, multiplied by the J's component of the CTF of that image, and then you take the square difference. And you divide it by the variance of the noise, which for that pixel J, which, as I just said, is expressed actually as a function of spatial frequency of the components J. Now, the million-dollar question then becomes, what do I have in terms of prior information in the absence of any experimental data? So what do I know about my reconstruction without having done any experiments? Now, you might know it's homologous to a given structure, and that would be very powerful prior information, but it would also be very difficult to express that kind of information in a very general framework. So instead, I opted for a much less informative prior, and in assuming that also the signal in our reconstruction is Gaussian distributed. So every Fourier components of the 3D Fourier transforms of the reconstructed maps are Gaussian distributed, and they're all independent. And then the assumption is that they're all centered on zero, because they're in the complex plane, that they're equally likely to stick one direction as the other, so their expected value will be mean, but they also have a limited variance, and this is now this parameter tau squared here, again expressed as a function of the spatial frequency nu of each of the Fourier components of the map. And by limiting the power of the Fourier components in the reconstruction, we actually impose smoothness in the real space. So this is a smoothness prior in real space by limiting the power of the reconstruction in the Fourier domain. And this is just how you express it. It's again a Gaussian function, multiplication over all L Fourier components of the model. It's centered on zero, so it's really zero minus whatever the value is. Okay, now if you combine that prior and the likelihood function we just discussed, and you marginalize over all these orientations phi and perhaps the class assignment k, and you plug all that into this regularized likelihood function, and you then apply a simple expectation maximization optimization algorithm, then you get to the following algorithm. And we won't go through all the details, but I would like to discuss the main features of it. First of all, we will estimate the variance of the noise in the experimental images, again as a function of a spatial frequency, directly from the data itself. And it's actually doing that by taking square differences between the actual the experimental image. You subtract the CTF affected projections of the reference in the right orientations from them, and you look at the power of the differences, and that's basically it's what the power that's left after subtracting your assumed signal is being considered as the variance of the noise. And similarly, you can estimate what's the power in my reconstructed signal just by calculating exactly that. Just calculate the power spectrum of your reconstruction. And if you have these two values, you can then calculate the updated reconstruction for the next iteration using this equation. And for those of you familiar with equations for Wiener filters in single particle analysis, you'll recognize that this is a variant of a Wiener filter, in that it's a summation over all the images multiplied by the CTF, and it's divided by a sum of the CTF squared values. And then in a perhaps more traditional Wiener filter expression, you would then have plus 1 over the signal to noise ratio. I think that's not necessarily correct. And I think the correct way of doing it is that you actually have to divide each of the CTF affected images by the variance of the noise, and you have to divide also the sum of the CTF squared by the variance of the noise, and then the additive factor here becomes 1 over the variance of the signal. So that equation then becomes central to the Relion reconstruction, and it becomes a Wiener filter in the true sense of its definition, that it becomes the best possible linear filter of your reconstruction. So the reconstruction that is calculated will have the least possible amount of noise under your statistical assumptions. And because of the way it's constructed, it will be able to handle uneven rotational distributions. It can handle astigmatic CTF, CTF's envelopes, etc. And the effect of it will not only correct for the CTF, which many people think is the function of a Wiener filter, but it will also automatically low-pass filter your reconstruction. And that low-pass filter effect is because there is a variance of the noise, the sigma squared, which falls off with frequency in a certain way, and there's the variance of the signal, which falls off with frequency in a certain way. And if you're at very high frequencies, there is a lot of noise compared to signal, and then because here are the inverses, then this term becomes much larger than this term, and the reconstruction gets squeezed to the power of the reconstruction gets squeezed to 0. If you're at very low frequencies, then the noise terms in the data are not so large compared to the signal in the data, and these terms are much larger than these terms, so that the reconstruction is basically unregularized. So the Bayesian algorithm thereby, as you like, balances between prior information and experimental information. It will calculate by itself signal to noise ratios in your data and use those to optimally weigh the alignment functions and also the reconstructions when you calculate those. And all that is done without arbitrariness. So there's no parameters for the user to tune. And I think that's one of the main advantages of Relion. So that brings me to some comments on using Relion. This is the the address of the Relion wiki, and I would definitely recommend everyone who wants to use Relion to start there. There is a link to a tutorial. Do that one first. There is a test case on beta galactosidase images. You can just go through it, and I think that's the easiest way into becoming an expert in Relion usage. Then this is the Relion GUI. The central programs of Relion are actually the 2D, 3D classification and the 3D auto-refine. So I'd like to, and that's actually the regularized optimization, likelihood optimization problem that I've just discussed. So I thought I made a few comments about the implementation there. The 2D class averaging, 3D classification, and the auto-refine all use the exact same code. They all marginalize over the classes. In the cases of 2D classification, they marginalize also over the in-plane rotations and the in-plane translations. And then in the cases of 3D refinements, you also marginalize over the out-of-plane rotations. And in both 2D class averaging, 3D classification, and 3D auto-refine, you can then calculate CTF-corrected reconstructions, either 2D class averages or 3D reconstructions, from the data using using the equation that we just had up there. Now, an important difference between 2D classification and 3D classification or refinement is that the 2D problem is simpler. The convergence behavior of the algorithm is much better, and you can actually start from random orientational assignments for all your particles and only provide a number of classes that you want, and then the program will, in most cases, converge to a useful solution. Now, and that's not true for 3D refinements, and I'll come back to that in a minute. So the 3D auto-refine is very much like 3D classification with a single reference. Again, it uses the exact same code, but there's two important differences with 3D classification. And the one is that it will estimate how accurately you're aligning particles with respect to your reference, and then automatically go to finer and finer angular and translational samplings of all these hidden parameters of the orientations of each particle. And it will do that for every given sampling rate. It will do a few iterations until the resolution doesn't increase anymore. Then it will see, can I still refine my particles more accurately based on current estimates? If the answer is yes, then it will use an even finer sampling. If at some point the answer becomes no, then the program will converge. Now, the second difference between auto-refine and classification is that you can estimate these values tau squared, the power of the signal, not from the reconstructions themselves, but also from a gold standard Fourier shell correlation curve between two independently refined maps. And by doing that, you can close the door on inflated resolution estimates inside your refinement procedure, to which in principle the 3D classification itself would be sensitive, because you estimate the power of the signal from the data itself. So you might start to overestimate it, thereby allow too high resolution components into your reconstruction. Then the next iteration, overestimation will be worse, etc., etc. So to put a break on that, you can estimate the power of the signal from these gold standard FSC curves. Okay, and that then results in no inflated resolutions due to overfitting. And because of the automated way in which you increase the orientational sampling all the way till convergence, you get then very high resolution maps, but with a minimal user input. Okay. One important thing to realize is that the expectation maximization algorithm is a local optimizer. So, as I said, for 2D class averaging, you can start from random orientation and just provide numbers of classes. But for 3D refinements or classifications, that will often not work. So if you start from all your particles in random orientations, then your initial model will look basically like a blob or a ball, and refinement in Relion will then likely get stuck in its nearest local minimum, which is very often not not useful. So that means you need an initial model to start 3D refinement in Relion, although that initial model only needs to be at relatively low resolution. So the fact it's a local optimizer then also means that if bad models goes in, a bad model can also come out. So Relion is not a solution to get away from an extremely bad initial model. Especially common lines models, because they're created from the data themselves, they're kind of consistent with the data in certain nasty ways, in that if they're very correct, they're notoriously difficult to escape from. And I think there's currently better approaches. If you're not sure about your initial model, you can use randomly perturbations of your optimization procedures. Something like simulated annealing has been used lots in X-ray, and those algorithms can potentially reach global minimum. Although also they are never guaranteed to do so. It does mean that sometimes these algorithms, you can start from random blobs and then refine the structure towards a correct solution. I think two very popular solutions that people use, also people here at the LMB, are the program Simple from Hans Almlund and EMAN2, about which Steve apparently will speak next month in your series. So I would say they're increasingly popular and they're powerful, but you have to be careful, because they potentially reach the global minimum, means they can also get stuck in a local minimum. And then you get to this situation where bad model in may be bad model out. So you have to be careful. Although I do think that with the advent of these new detectors and much higher signal to noise ratios, the problem of finding a good initial model is going to be ever less important, because we see that if we don't see any secondary structure elements in our models, in our reconstructions, something must be wrong, perhaps the initial model. So what we typically do, we run simple or EMAN for many different trials on our data until several of them start falling into the same solution, in which we start to see secondary structure elements, and then we know we're on the right track. So whereas previously on lower resolution maps, initial model could be a problem, I think with high resolution structure determination, this is ever less the case. And these simple and EMAN2 approaches are very powerful ways of getting your project started. Good. To finalize, I thought I'd just give you some comments of what we usually do in Relion, in the hope that's useful for some of you. Particle picking, we typically pick some micrographs, and then it depends on the patience of each of the users, by hand, because it's a very good way of getting to know your particles and your data. And if you've picked by hand, you'll be better the next time when you sit behind the microscope to see where your particles are, etc. Do interact with your data. Do not do everything automatically, would be my advice. Then we calculate reference-free 2D classes from those manually picked particles and use those as templates for auto-picking, because we typically now have thousands of micrographs for a project, and picking them all by hand would just basically be much too much work. We do that in Relion now as well, and then we use a sorting algorithm to detect outliers, and it's explained in the tutorial what that does. So if you then have your auto-picked coordinates, we do like to quickly go through many of the micrographs, if not all of them, just to see that the auto-picked coordinates make sense, and if there's obvious outliers, we can remove them with the middle mouse in the Relion picking GUI. My general advice for particle picking would be, don't be too greedy, because smaller, cleaner data sets are better than very big, dirty ones. And the major thing you have to watch out for if you do template-based auto-picking is Einstein from noise artifacts, where characteristics of the templates are found in the noise-only micrographs even, or your micrograph can have particles, but even in the noisy regions, you may start to see the program may think there's templates, and if you average over many noisy instances, then you may get your templates back. So typically this then results in 2D classes after auto-picking that are very low resolution if you've used low resolution templates to auto-pick. And that's something I would always recommend to prevent you getting a 3 angstrom structure out of noise-only micrographs, because you've actually looked with 3 angstrom resolution templates. You should just filter your templates for auto-picking to 20 angstroms, so you know that whenever you get signals beyond 20 angstroms, that's not a effect of model bias. I just wrote a paper in Journal of Structural Biology on the auto-picking procedure in Relion, and the Einstein from noise problem is discussed in much more detail there. So I'd recommend reading that one. So for 2D classification, we always do 2D classification when we get a new data set. And one of the main aims is to just tidy it up, get rid of bad particles, and just see which particles average nicely together with other ones. It's also the major, I think it's the best, it gives you the best impression of how good your data will be. If you start to see all kinds of secondary structure elements in your 2D classes, you know 3D reconstruction should go well, provided you have enough different views. If something is already wrong at the 2D class averaging stage, you will not going to get high 3D reconstructions either. So often you then see large classes which are very high resolution, and smaller classes which are lower resolution with crap, and those we all just throw away. Okay, and you can possibly repeat that, although you should perhaps not do that too much. Then after 2D classification, you can go into 3D classification. we almost always do that one as well, because almost all samples are heterogeneous. I don't think there are many macromolecular complexes in nature that actually are rigid as a rock. And then computational costs, they're often limited to 4 to 10 classes, although I've seen people doing 20 class refinements. The main scenarios there is what we call an exhaustive angular search, where you search for all possible relative orientations of the particles in a 7.5-degree angular sampling rate, because if you go much finer, it will be very expensive. And you do that and you refine 10 different models at the same time or so. If the structural heterogeneity is somehow much finer than what you would be able to find with a 7.5-degree angular sampling rate, then you need to use finer angular samplings in your classifications. The way we do that without spending too much CPU time is typically to first do a 3D auto-refine using the entire data set, and thereby you get a consensus reconstruction, which may be fuzzy because of structural heterogeneity, but at least every particle will be assigned a top view or a side view. And then you use that output data.star file as input into the classification, and you then do local searches around the angles that you found from the consensus refinement with a much finer angular sampling. And now, since recently, we've also started to do a much more extreme version of that. Just keep all the angles from this consensus refinement completely fixed and only marginalize over class assignments. So you take the integrals over phi out of all the equations that I showed you. Especially if you do that within a mask focused on a specific area of the protein that you're really interested in, it's very good for classifying things in a focused manner. For example, the presence or absence of a small factor on the ribosome, you might still be able to do this with this keep angle fixed option. Then 3D auto refine, we almost do that once we get a homogeneous subset, or to get this consensus model, like I just said. And the important thing there is to always start from low pass filtered maps. It will use a gold standard separation, refine 2 maps independently, but the initial starting model for both independent refinements is the map that goes into this procedure. So if you start from a very detailed map in the 2 independent refinement, then model bias will keep those 2 detailed maps perhaps the same, and you get again incorrect resolution estimates. And also, low pass filtered maps give you the possibility to better escape from local minima should your initial model be wrong. Okay, then after auto refinement, there is an option in Relion for post-processing. That's an important thing because the resolution in the refinement of Relion is only based on unmasked Fourier shell correlation curves, and they underestimate the true resolution of your map. So in the post-processing, you'll get a much more correct estimate of the resolution, and that's usually a value you will like much better. It can also correct for MTF of your detector and use automatic B-factor sharpening for higher resolution maps. Then movie processing. We now almost always start with the motion core scripts from Xu Ming when he was still at UCSF to do a per micrograph based motion correction. Then we do initial 2D, 3D classifications, auto refine, and then we do movie processing without rotation and use this new particle polishing approach, which I published last year in eLife, to do per particle motion correction and also radiation damage weighting for the independent movie frames. Now, if the reconstruction that you have doesn't really go much beyond, let's say, 7 or 8 angstroms, then that might not be so useful because it will be very difficult to estimate B factors for the individual movie frame reconstructions. And then after you've done particle polishing, you now have particles with increased signal-to-noise ratio. So they will be better for 3D classification or at least always rerun than your 3D auto-refine. So I think that brings me to the end of this presentation. I'd like to thank you for your attention. And because I understand you're all web-based learners because you're in this webinar, I thought I'd put up this a reminder of that we also have an online course on the theoretical aspects of cryo-EM structure determination, and you can download videos of the lectures from this FTP site. And I thank you for your attention. I'm happy to take questions.
Great, thank you very much. If anyone has questions, feel free to pass them on in the chat window, or anyone in the room. We have a local audience here, so here ask questions. So I have, well, not so much a question, but so from 1.2 to 1.3, you introduced a bunch of new features into Relion. I was wondering what's on the roadmap for 1.4. Could you say more about maybe what you're working on, things that you're kicking around in your code?
Yes. So Relion 1.4, which we're currently testing, will be released around May or June. Usually I do this around the Gordon conference on 3DM. We'll be able to do subtomogram averaging. So not only work with two-dimensional projection images, but also three-dimensional subtomogram data or random conical tilt reconstructions, whatever kind of three-dimensional data you would like to average together. So that's the main functional improvement in Relion 1.4. And then I've spent some time on speeding up refinement in 1.4 as well. So overall code will be about 30% faster of this refinement code, whereas movie processing will be up to a factor of 10 faster than in Relion 1.3.
Wow, that sounds fantastic. That's great.
And then ongoing projects, which will be at least a year and a half of, is helical processing in Relion, and we're also starting to think on how to deal with continuous form of structural heterogeneity. But as I say, that those are unfinished projects; they're still ongoing.
All right, great. Well, thank you very much. With that, we'll wrap up, and I'll follow up with you online. Thanks again for joining us, and great. Thank you.
Okay, my pleasure. Thank you. Bye-bye.